Fantastic. Yes, Alex, thank you so much for giving me this opportunity. I have been asking for an opportunity to do that for quite some time. So, yes, I am extremely happy to be here. It's one of those topics where, it sits between the technical domain and the business domain, and as people may know me a little bit, I've been with Neo4j for a decade now. So that I sit between those two domains a little bit as well myself. I love business, I love sales, I love building solutions for clients, but at the same time I'm also someone who likes to hack with Cypher, and have some fun with that. So I'm in between those two things as well, and that's basically the reason why I wanted to do this talk, because what I've been seeing in with talking with clients and talking with users is that it can be quite difficult to get a graph project up and running. There's some symptoms that we see time and time again. Like in the early stages of a graph project, everyone's like super enthusiastic and yeah, this is fantastic and this is so innovative and this is so new and let's get going with it. And then all of a sudden that enthusiasm seems to die out a little bit. And then all of a sudden you get these messages. Yeah, we're going to do it next year, or it's not a priority today, or we don't have a budget for it, or whatever, or the current solution is good enough. All of these excuses for not getting going with graphs, right? And that bothers me, not just because I'm a commercial guy. No, really, it doesn't bother me because of that much, really. But at the same, I really do get annoyed by that, because it feels like it is hampering innovation. It's really stopping us from making more progress. And then I ask myself, what do we know here? What is real and what is already material here? And there's a couple of things that we really clearly know from talking to people, from working with clients, but most of it is actually in the technical domain, right? So we know this, we track this, we understand this. Graph databases, graph platforms are primarily adopted by technicians, and they look for technical benefits. That's normal, right? And one of those technical benefits, one category of technical benefits, is actually more long-term oriented. It's all about ease of modeling, or flexibility, or it's a natural fit for our domain, or those types of things. Like these long-term benefits that are real, right? But they're not necessarily driving like immediate decision making, right? Now, fortunately, in the technical domain, there's a second category of benefits that is actually very, very immediate. It's all about speed. Right? With a graph platform, you can do stuff that you can't do with other platforms, because it's just way more efficient at doing that, right? It enables these workloads that we thought were impossible before, and all of a sudden they become possible, right? And because of that efficiency, there's obviously also hardware and operational savings that we can immediately quantify. Right? So there's these long-term benefits, right? And there's these immediate technical benefits, but they're both quite technical, right? Which is why it's important to try and realize that we also need to convert this into a business story, right? We need to try and relate those technical benefits to a value case that is more business-oriented, right? That people that have no technical background will understand as well. And very often that means that we're going to apply this. We're going to apply this to a very specific use case. And even better than that, we're going to apply it to a very specific industry, organization, and even person, right? Because we want to have a very specific conversation with those people around the benefits of implementing that technical platform that we offer, right? But here's the thing, even when we realize that, even when we do that, even when we apply these things that we already know, we still faced with a number of issues, and which is why I'd like to spend the next couple of slides and the next 10 minutes or so trying to explain what we don't know yet and what we need to think about a little bit more. Because reality is, and I'm going to try and peel this onion a little bit, right? Reality is that right now, in this economic environment, if you're going to spend six figures, on a graph project, you better have a value case. Simple as that, because otherwise you're not going to be allowed to spend any money. You might be able to spend 5K here or there, but you're not going to be able to spend a significant amount of money on the infrastructure that you need to build a graph project, right? The second thing is, that even if we as technicians, we realize that there's these technical benefits, that doesn't mean that the other side understands that the people that hold the purse strings actually understand that, right? Being right is not the same as being understood to be right, right? We have to explain this. We have to articulate this to these people. And of course, the technical value just isn't the same as the business value. We have to get to know the business results, the business impact that this technical value is bringing to the table, that it's enabling. And then the last point, which is probably the dearest to my heart, I've been living by this for a very, very long time, is that we should realize that our decision makers have a very, very specific way of dealing with uncertainty. In fact, humans have an interesting way of making decisions in times of uncertainty. When you're buying a graph database, when you're implementing a graph project, you're doing something that you've never done before. Most people have never done this before, right? So as a consequence, they're making decisions with lots of uncertainty, right? And here's something that I'm hoping people have heard about already. Nobel Prizes have been given for this, and it's really, really interesting behavioral economical research, right, which is called prospect theory. When humans are faced with uncertainty, right, and this is not up for debate, this is just science, this is proven, right, they always underestimate the value and overestimate the risk or overestimate the costs. That's how we are wired. From the earliest days in the savannah, we were wired, we were grown, we were evolving to be like this, right? When we face uncertainty, when we don't exactly know the data, we're going to behave like this, right? And this is why, when you buy something new, when you buy something that you've never bought before, and you're faced with that uncertainty, you're going to actually be reckoning with this. My personal story here is always the same one. It's about this beautiful little car. This is the first car that I ever bought. Opel Corsa, right? Back in the 90s. When I just graduated from school and had my first job, and needed to get into the commuting game. It took me months to make up my mind. It took me months to make up my mind about, what car I was going to go and get. Why? Because I had never bought it before, and I was being faced with uncertainty. That's just how this works, right? And there's some really interesting research and some really interesting literature about how to apply this when you want to build a value case, right? So I have read a lot of books about this, and the best summary that I've found is in a book called Selling is Dead by Mark Miller, right? It's actually almost 25 years old now, but I still think it's super, super interesting because it applies to how humans deal with prospect theory, deal with uncertainty when they want to buy high technology, right? What Mark Miller basically says is this very simple equation, right? If the perception of value, PV, is not significantly greater than the sum of the costs, right? The monetary costs and the perception of risks, right? Then people are going to decide not to decide. They're just going to postpone it. They're going to stay with what they have, right? Because of uncertainty, if this equation doesn't hold true, they're just going to postpone the decision. And this happens all the freaking time. We see this enthusiasm at the beginning of the discussion with our users, right? And then all of a sudden they're like, yeah, maybe, next year, that type of thing. So if this holds true, if the perception of risk and the perception of and the costs need to be smaller than the perception of value, then what we need to do is we need to try and influence that. We need to work with our stakeholders. We need to work with our colleagues in our organization and try to influence this perception of value and this perception of risk. So how do you do that? Right? How do you build this case, and how do you influence these two factors? Well, I think that much of this is actually down to reducing the uncertainty by making it explicit. Right? Make it explicit that what the value is. Make it explicit what the risks are. And of course, make it explicit what the costs are going to be. And you should realize that both on the risk side and on the value side, you're going to have quantitative factors, right? Things that you can jot down and that you can calculate and that you can objectively find hard measures for, right? That are not going to be easily disputed. But there's also going to be qualitative factors, soft factors, right? That are going to be less measurable, right? Including feelings and emotions, right? So we're going to have to deal with those. We're going to have to deal with those. And how do we do that? Well, I think the first thing that we do is we have the explicit conversation with our stakeholders, right? We have to help them. We have to help them, and we have to help them create these value cases by having a conversation. They don't always know the answers to it, but at least then we know that they don't know the answers, right? And we're always going to ask them, how are you going to justify this? And ask for specifics, right? And the key word, the key magic word that I've always used here is why. Why are we doing this? Why is this use case so interesting to you? Okay, because it will change the way we do things. Okay, why does it change the way we do things? Oh, because it will allow us to follow a better process. Okay, why will it allow us to follow a better process? Oh, because we won't lose that much time. You see what I'm doing here? Right? I'm constantly peeling the onion. Why? Until we get to something measurable, ideally. Until we get to something that we can write down on a piece of paper and say, this is why. This is why we're doing this. Right? So this is the most powerful word in the world. When you're trying to uncover these graph value cases, you want to ask questions. You want to engage in a conversation with the stakeholders and find out why. Another really powerful phrase that I'd like to suggest is, how are you doing it today? Okay, so you have this idea of this new use case. You think graph technology might be really interesting. How are you doing this today? Right? And dig into those processes. How do they work? Where are the issues? Where are the challenges? How do we improve this? How does the technology help with those improvements? Have there been any highly visible incidents, for example? Right? How are you doing this today? And who is impacted by those existing ways of working? Maybe it's other groups, maybe it's customers, maybe it's external people, maybe it's internal people, maybe there's a really important merger and acquisition, a critical business initiative that's going to be impacted by this. Okay, so how are we doing this today, and who's impacted by this way of working? And hopefully, we will find specific factors. We will find specific factors that we can use to influence the perception of value, like, for example, reduction in hardware, shorter response time, real-time capabilities, fewer support calls. There's no limit to what this might be, right? And same thing for the perception of risk. Hopefully we will also find, specific ways to do that, right? We can, show them other case studies. We can have them call people. You can work with a partner, whatever it is, right? So there's specific ways to enable this. I'd also like to point out that their second big way for you to build this graph value case, right, aside from having the conversation with your stakeholders, asking them why, asking them how they're doing this today, the second big way of doing it is really to dig in and to do your homework, right? And prepare for this explicitly. Don't assume that someone else is going to do this. So I would offer and I would recommend that you talk to people. That you talk to people that have done this before at the FOJ, in the community. How did they do this? Do they have examples? Do they have inputs, right? And you can also rely on stuff that we have actually prepared. Obviously, it's in our interest to enable you this way. And we've worked with, for example, Forrester Research, right, to build something called a TAI study, Total Economic Impact, right? So this is how you can actually look at some examples that Forrester has validated that basically says, this is how you justify a graph project. And we've actually done some spreadsheet work for you, right? We've actually tried to summarize this in a couple of Google Sheets. You can get these from your local Neo4j contact if you want, for recommendation engines, for master data management, for cybersecurity, for all these use cases, we have examples of how you can do this, right? So I'm going to wrap up. I'm at the 15-minute mark, I think, and I'd like to wrap up by saying, please don't stick to just the value, the technical value, right? Think about the business impact, right? Think about the fact that, people are always going to underestimate the value and overestimate the costs, right? And that this quantification step of value and risk is a really, really great way of reducing that uncertainty. Write it down, make a document out of it using, for example, the template that we can share, the Forrester template or a simpler version of that. And please, like Emily used to say, don't be a lonely document, right? Don't do it on your own. Connect with others that have done this before and use the material that's already there. With that, I'm going to wrap up and thank you for the opportunity of doing this talk.
Very cool. Thank you very much, Rik. Lots of love in chat. I hope now everybody understood how the emojis work. So I like to see them now. We had a couple of comments. So I'll post one in from Chris. Chris says, prospect theory is fascinating as a business technologist who has 100 million plus business cases. This is so true. One good technique is foot in door. Instead of huge business cases, do small business cases that build on success.
Yeah.
That's a good...
Walk before you run, right? I mean, that's a really great recommendation in any case. And, I had one of my earliest mentors that used to say, if you want to eat an elephant, don't try it in one piece, which is, it's obviously a really gross way of saying that, you walk before you run. But I think this is very true and build on successes like that. Yeah.
Yeah, that's very cool. There is one funny one from Matt. They call it the I'm not pronouncing it. So high interest and stall.
Yeah. That's a really good one, Matt. Yeah, I'm going to remember that.
Constantly peeling the onion is very important. So a couple of people also say that. Yeah, lots of love, lots of clapping and thumbs up. So really good. I see you now got it to work. It's great. And then, there is maybe one tip from Stefan here. Very huge. It doesn't really render here in the stream, but if you want more, you could always check out post number 1 of how to make sound strategic decisions under uncertainty. Is that a podcast? I'm not 100% sure. But
you know what, Alex, if I may add, myself and Stefan, we actually had a lot of fun in full pandemic working on a set of podcasts and articles, and they're available at graphvalue.com. There's some good material there.
Sounds good. Okay, cool. Thank you very much, Rik. Need to wrap it up for the next one. Thank you for presenting today, Rik.
Thank you.
So today I'm going to talk to you about CloudScreen, a graph-based drug repurposing platform empowered by machine learning. I would like to start by presenting some general information about our platform and our machine learning approach, and afterwards my colleague Sotiris will demonstrate some code and queries for each step of the pipeline. And then, if the time allows, we can take some questions and discuss. But first, what is drug repurposing? Some of you may know that drugs work by physically interacting with and altering the function of specific proteins in our body. Specific proteins are linked to diseases and their outcome. In the human body, there are approximately 20,000 proteins, consisting the entire proteome, from which only a fraction is known in terms of structure. So basically, drug repurposing is the process of uncovering new target proteins or indications of approved or abandoned drugs for use in a different disease. When it comes to drug repurposing compared to traditional drug discovery, the comparison says a lot. Repurposing drugs have better success rates, less safety concerns, fewer years to impact, and much fewer costs. So, as you can imagine, it's a really important technique in the field of drug discovery. CloudScreen is a graph-based platform developed with Neo4j by CloudScreen Private Company and the Biomarker Discovery and Translational Research Laboratory of National Hellenic Research Foundation. CloudScreen integrates two types of data, 1D biomedical data and 3D structural data, and feeds them to an AI predictive algorithm in order to produce effectiveness and toxicity predictions, which will be experimentally evaluated, leading to new indications. Now, the field of drug repurposing has several limitations on how it has been approached. Most solutions are heavily based on textual data, while we approach the problem by incorporating 3D structural protein information, focusing at the molecular level. Existing protein structural information account only for 20% of the proteome, while we are curating and implementing 100% of the proteome space. Also, there is a vast amount of contradictory information in existing scientific data. We are trying to tackle this limitation by our own machine learning algorithms. 1D biomedical data in CloudScreen concern information extracted from track patents by applying name entity recognition, data collected from clinical trials, the clinical significance of protein variants and their disease associations, pathways related either with a protein or a drug, pharmacogenomics information, data related to pharmacovigilance, information about protein disease associations, and drug activity from experimental data. 3D structural data include the structure of approved and experimental drugs, the experimentally known structures of human proteins, homology models of missense mutations of proteins forming the human variome, AlphaFold models with high confidence allowing us to explore the human protein, and molecular docking calculations of the approved and experimental drugs upon the proteome and the variome, allowing us to map the interactions between drugs and proteins. Molecular docking is a molecular modeling method which predicts the preferred orientation of one molecule, one drug for example, to a protein's binding cavity. The 1D and 3D data have been integrated in a graph database employing Neo4j. The core of CloudScreen is the 1D data which form a knowledge graph. The core knowledge graph is further extended by the addition of the structural 3D data extracted from visual screening. The knowledge graph has been designed by integrating data from public repositories, while the 3D data come from in-house calculations performed in a high-performance computer. The graph database was selected since it was the best way to represent the complex interaction of biochemical data. Yet, storing all this information in graph format has also assisted in better visualization and analysis of the data. It is important to mention that during the development phase of the CloudScreen platform, we found that the graph database is easily expandable. Nowadays, artificial intelligence constitutes a crucial part of the data analysis routines. We can define artificial intelligence as the development of systems and machines that carry out tasks which typically require human intelligence. In data science, where data is transformed to information, machine learning, which is a branch of artificial intelligence, is applied in order to produce accurate predictions that can guide decision-making without human intervention. Machine learning utilizes that data to recognize and learn hidden patterns which cannot be easily detected by humans. To this end, the graph-based machine learning is used to process network data, leveraging the power of the relation between entities that can be used for predictive modeling and analytics tasks. The main challenge in graph machine learning is the transformation of the network to a tabular data, which is usually done through node embeddings. Graph machine learning can have many applications, with the most common ones being node classification, link prediction, community detection, and node regression. CloudScreen utilizes graph machine learning as an extra layer of validity to the predictions that it provides. More specifically, the outcomes of the main queries that the platform has are further combined and filtered through the graph machine learning predictions. The purpose of CloudScreen is to provide suggestions about drug repurposing candidates. This is done either through a drug query, where the platform provides the new targets for existing drugs, or through a protein query, which results in drugs that possibly target the queried protein. The results of those queries are mainly guided by molecular docking results. So the graph-based machine learning is used complementary to the docking calculations. These two technologies combine the molecular and topological features to provide and integrate highly accurate prediction. CloudScreen applies graph machine learning for link prediction in order to identify probable drug-protein interactions, drug variant interactions, and drug disease interactions. The steps for the proposed graph-based machine learning pipeline are the following. At first, we need to have set up a knowledge graph. In our case, it has the known drug-protein interactions and experimental data for the activity of a drug to a protein target. Then, the features of the graph should be extracted to quantify the topological drug-protein associations. So, feature engineering is applied by implementing node embeddings to transform nodes to vectors. Since the nodes are either drugs or proteins, in order to quantify the interaction, the vectors produced by each node type should be combined. The feature combination is done by geometric approaches that will be explained later. Having the feature vectors for each drug-protein interaction, a matrix is designed, which is preprocessed before machine learning. The main preprocessing steps are duplicate removal, data normalization, splitting the data into classes, and then dividing the data into training and test sets. Then the training of the selected machine learning algorithms is performed, and the trained models are validated upon an external holdout test set. The test set is used to evaluate the model's performance and generalization capacity. Having an accurate and robust model, we can perform predictions in a set of drugs and proteins of interest. Finally, the resulted predictions should be further analyzed to identify the most probably repurposed drugs. So, for the feature extraction, we perform node embedding techniques. Node embedding is the process of transforming a node into a vector. Currently, Neo4j supports three types of node embeddings. FastRP is a random linear projection algorithm which projects n number of vectors of arbitrary dimension into all number of dimensions and still approximately preserve pairwise distances among the points. GraphSage is an inductive algorithm which utilizes node feature information to generate node embeddings by sampling and aggregating features from a node's local neighborhood. Node2Vec computes a vector representation of a node by sampling a neighborhood through random walks in the graph. Then the algorithm utilizes these random neighborhood samples to train a single hidden layer neural network to predict the likelihood that a node will occur in a walk, based on the occurrence of another node. For the feature combination, several techniques can be used. Some of them are vector concatenation, vectors Hadamard product, weighted L1 normalization, weighted L2 normalization, and cosine distance. The calculation of each technique is shown in the results column here. For the training and the validation of the model, the initial dataset, which has both positive and negative classes, is splitting in training data, which consists the 70% of the dataset, and test data, which represent the 30% of the dataset. The model is trained by tenfold cross-validation and applied in the training dataset. And then the resulting model is evaluated against the holdout test set. So in a few, the final model can now be used for the link prediction in unknown drug protein pairs. The prediction of a new link will indicate a new target for an existing drug, enable drug repurposing. The new link predictions should always be experimentally evaluated. So, in a few words, using Neo4j, we accomplished to integrate 1D and 3D biochemical data inside the knowledge graph and then combine the docking results with graph machine learning in order to develop a drug repurposing platform for intellectual property generation. And now it's time to hand you over to my colleague Sotiris for the demonstrating part of our session. Thank you very much.
So, hello everyone. Now we're gonna proceed with the demonstrative part of the session. Let me share my screen. So, you can probably now see my screen. We will begin with a quick overview of our platform and some statistics. So, as we can see from this query, we have approximately 300,000 nodes in our graph, whereas we have approximately 19 million edges, which represent the relationship among our nodes. More specifically, we can see in the above query that we have 33 type of nodes, which represent 33 different heterogeneous open repositories from which we have collected our data. So we have 92,275 proteins in our platform and 14,316 drugs. So we can imagine that the amount of data is very large, and the docking experiments that were done in all this amount of proteins and drugs resulted in some 100,000 of dockings. So we can see here the number of nodes for each type of database, the average number of properties per node, the minimum number of properties per node, the maximum number of properties per node, and the equivalent statistics for the relationships. Now we're gonna proceed in the graph machine learning part. But at first we have to understand the type of data that we have aggregated in order to perform the graph machine learning. So I will begin with a query that returns the drug protein pairs, which will be used for the positive class. As a positive class in our graph machine learning pipeline, we mean the pairs of the marketed drugs and proteins. So in this case, we can see that we have subgraphs that contain a blue node, which represents the drug, and a red node, which represents the protein. We can see the connections among drugs and proteins, which are the known connections. Its drug node, its blue node, has some properties. If the drug has been approved or not in a specific protein target, which is used in our pipeline in order to collect only the approved drugs for specific protein targets. The second part of the knowledge graph that we are using in our machine learning pipeline is the data for the negative class. As negative class, we define the protein drug pairs that are not successful. These data are mainly retrieved through experimental evaluation from public repositories. So here we can see again the blue node is a drug, whereas the red nodes are again proteins, but this time the edge that connects the two nodes carries the information about the experimental evaluation of the drug in the specific protein target. So we have used a cutoff, which will be shown later on, in order to define only the failed experiments in order to represent the negative data. So, excuse me. All right. What we have performed in our pipeline is the integration of the Neo4j platform with VR Studio. We have specifically connect RStudio with Neo4j in order to retrieve the data in R and perform the analysis in the RStudio. So the connection is done through this chunk of code where we use the Neo4R driver, and it is the first step of our pipeline. We have to connect to the knowledge graph database in order to retrieve the data. The second step is to query the drug protein pairs, which are about the positive class and contain the known pairs of marketed drugs in specific proteins. Whereas the third step is projecting the above graph in the graph catalog. This projection step is very critical to be performed since we use the graph data science library of Neo4j, and we should perform this projection in order to apply the node embedding algorithm later on our pipeline. So the node embedding algorithm that we used in our case is FastRP. We have also implemented node2vec, and we will provide the results later on. So in this way, we perform the FastRP query in order to generate the node embeddings and transform our nodes into vectors. The fifth step of our pipeline is now to combine the vectors that we have produced. We should take into consideration that each node of the graph is described as a vector, so we have no connections, we have no data about the connections of drug and the protein. So by performing Hadamard dot product, we combine the node vectors from a drug with the node vectors from a protein, getting the features that describe the relation of the two nodes. The sixth step is querying the experimental data in order to create the negative class. In this case, as you can see here, we have put a threshold which refers to 10,000 nanomolar, which is a metric used in the experimental data, in every type of experimental data, and the metric that they evaluate, which can be EC50, IC50, or KI. And in this way, we retrieve only the experiments that have failed in specific drug protein pairs. Then we use the retrieved data in order to find again the feature vectors that we have previously imported. So this is the eighth step where we proceed to the machine learning pipeline. Here we see how we format the negative class, which represents that drugs that cannot be used in a protein, and the positive class, which are the drugs that are used in a protein. In the ninth step, we split the data in training and external test set. The split is done with a 70% of the whole data set. So we take the 70% of the positive class and the 7% of the negative class in order to design the training data, while the 30% remains for the test set. The data are random sampled. So the final step of the pipeline is to train our machine learning algorithms, which is, in this case, our random forest, support vector machine or HVM, k nearest neighbor, or as it's known as KNN. So we train those three machine learning algorithms using k-fold cross-validation. What we have achieved with this pipeline, as we can see here, we have used two types of node embeddings and we have performed the same type of analysis. So for the node to vec, we can see that we get a very good performance for both for all the three classifiers. However, the HVM managed to outperform the other two. Yet we can see that in both 10 fold cross validation and test set, we have the algorithms fails in order to predict totally the negative class, which is the drugs that do not that cannot be used in a protein, while the sensitivity is still very low. While when we perform the same pipeline with the fast RP node embedding, we can see that we have a 10% increase in our accuracy, which shows which is managed to achieve a 96% performance and an equivalent performance in the test set, which indicates the generalization ability of our models, while the sensitivity and specificity in both 10-fold cross-validation and test set are in equivalent amount. These results indicate the ability of graph machine learning to be applied in a knowledge graph for drug repurposing. So this pipeline has been applied in a knowledge graph and has produced accurate and robust predictions. Those predictions are integrated with the docking results, providing new targets for existing drugs. Based on this pipeline, we have our first repurposed drug, which is now under experimental evaluation, and our first patent is on the way based on this platform. At this point, I would like to thank my team and colleagues that we have worked so many months on this project. And I would like to thank you for your attention. We are now ready to answer your questions. Thank you very much.
Yeah, thanks a lot for a wonderful session. So we have some questions. Let me point out. So it's a question from the Andrew. How many different kinds of node in the graph?
33. There are 33 different databases. So each of one of those 33 databases has its number of nodes. All the nodes are approximately 300,000.
Okay, thank you. Let me move on to the next question. It's a question from India. What do you think makes the graph interesting compared to the other machine learning?
Yes, the difference of this pipeline based to the other machine learning pipelines in the graph machine learning is the fact that we have used the negative class according to the experimental data. Most approaches that currently are employed just take a positive class, the known pairs, and they just mix the data and perform a random sampling. So in our case, we use experimental data as negative class.
Okay, so the next question was from Andrew once again. How do you extract the relation?
All the relations that have been added in the in the platform were collected from public repositories, were pre-processed, and they were added in Neo4j. And the way that were added was done in order with a simple query to get the relationships. So basically all the relations are from public repositories.
Thank you. So we have 2 more minutes. We'll go with 1 or 2 questions. Let me go to another one. So what do you classify with the models? I'm not familiar with this domain. The question from John.
So this we don't do exactly classification, but link prediction. We predict, we classify which drugs will bind to a new protein target and which drugs will not. So if we see the problem as a binary classification, is about linking a drug to a protein and a drug that cannot be linked to a protein. If we have an existing drug that is in the market that can be linked to a new protein, then we achieve drug repurposing.
Okay, so the last question, which one we have it, you have mentioned dot product of Hadmor gate. Isn't that the quantum gate?
It's the Hadamard product. It is like the no, sorry, it's the Hadamard dot product. It is like the dot product, but with not the summing part. It's only the pairwise multiplication, as it was shown in the slides.
Okay, so last question. So yeah, it's from Rohit Kumar. Can you provide the link of full ML algorithm integration with Neo4j?
The algorithm is not provided, but the pipeline can be reproduced according to the Neo4j documentation. If you would like, you can contact us and we can see how we can share the algorithm.
Okay, thanks for the wonderful session and also our time. Thanks to all the viewers. So we have another session. It's related to the knowledge graph. We'll be starting shortly. Yeah, please keep in touch. Yeah, thanks to all. Bye.
So welcome everyone. So as mentioned, my name is Chris. I'm a CTO at Grapher. We've been like developing and doing Neo4j consultancy for 10 years almost. Right. So today my screen will be mainly VS Code and the Neo4j browser because we'll spend more time in Docker Compose and some diagrams than in any slides actually. So yeah, the outline for today, we'll speak about a small anatomy of a Neo4j Docker container when it's running, how to access and control the container, making usage of volumes, some tips for configuring Neo4j on Docker, installing plugins, but also the life cycle of how Neo4j determines how to install plugins automatically. And we will show how to extend the Neo4j image for having your own plugins inside. As well, depending on time, I can also show a small demo of a Neo4j cluster on Docker. Right, so let's start immediately and go here. So to understand what a Neo4j Docker image is, you need to take the Neo4j Docker file that is provided in the Neo4j Docker repository. So as you can see here, they are using a Debian base image. They are copying the Java binaries from the Eclipse Temurin 17 image. So very important, Neo4j5 runs on Java 17, not Java 11 anymore. They're doing a couple of environments, system commands for creating the right user and the right groups. And then they install Neo4j. They set the working directory, they create some volumes, expose some ports, execute this file, the entry point.shell file, and then they run the Neo4j command that will be passed actually to the entry point. Right? What is important to understand is that a Docker image is actually the composition of many layers. Each line that you see on those in this Neo4j Docker file is actually one layer in the image. So if we look here, right? So here you can see every line is an image, is a layer, right? And actually, if we inspect the Neo4j 5.1 image, right? We will start it here. Right, we can see the same representation we have in the diagram, but for the Neo4j image, right? So if I would take this Docker file, right, we start from the bottom, we can see add file here. This is actually taking this line, then it has 80 megabyte. Then if we go a bit further, we can see here add user. This represents this line. Install the Neo4j binary. This represents everything here. So we can see here is 230 megabyte, so which is the size of the Neo4j tarball, actually. Then all the other commands here, right? They go back to here, right? So all those layers actually compose the Neo4j Docker image. What is important, if we go back to the layer diagram here to understand, is that those layers are read-only, right? They are completely immutable. And every Docker container, so a running Docker container, is composed from all those layers, plus an additional very thin read-write layer on top of those. This thin read-write layer is actually what makes possible for multiple containers, running containers, to use the same base image, actually. So if we look here, right, we can see that if we would have multiple Neo4j containers running on the same machine, for example, they will all be composed of the same image, of the same layers, plus the thin read-write layer. What is also important to understand is that whenever a file has to be modified from the base image, so in the base image, you can think you have the neo4j.conf file, the data directory, everything that we might want to modify will actually, at the time of modification, will actually be copied to the thin read-write layer and modified at that place. This is very important to understand because the performance of the I/O in this thin read-write layer is not very high, right? So it's like low performance I/O. So we will see how to improve this during the session, right? Right. So small summary. So image is composed of multiple immutable layer. A container reuse the layers, and also the Neo4j image exposed two volume layers. So very important to understand, data and logs. So if we look here at the and here volume / data / logs, right? So this is some hooks that we can use to mount volumes later. All right. So let's take a very small, simple Docker Compose file. Here, simple compose. Here, right? Nothing fancy. So it's the most basic Docker Compose you can have. We just specify the default password for the Neo4j user, and we accept the license agreement because we are using Neo4j 5.1.0 Enterprise. Very important as well is that you put the yes into double quotes, otherwise it will not be recognized thanks to the awesome YML format, right? So let's start this Docker Compose. So we will use the Docker Compose command, right? Compared to before, we're using the new Compose Go binary. So there is not anymore the dash between Docker and Compose, right? And we will just do upd. So we will launch the container in detached mode. So it will run in the background. Right now we can check the logs of Neo4j. Right, just for the remaining of this session, I will not for telling the logs, I will not write the full command. I have a small shortcut here. So here is the Neo4j container started. And actually, if I go to the Neo4j browser, if I refresh here, localhost 7474, we can see that Neo4j is running, and we have the default Neo4j database and the system database. Right? What is interesting to understand is that we can see in the logs already that there are some operations that have been performed. For example, we changed the password for the Neo4j user. We accepted the license agreement. We can also see that Bolt here is enabled on 0000, and as well as the remote interface is set up, which is interesting because normally Bolt is not listening to 000 by default. The server generally would listen only to local interfaces. And so I want to explain what is happening when the Neo4j container starts, actually. Right, so if we look again at the Docker file of Neo4j, here we can see at the end that the entry point contain a file that is called entrypoint.sh that will be executed when the container starts. I will not read line by line, but if you want to have a small overview of what this file is, so it starts here. You can find this in the GitHub repository later. But yeah, so it has a couple of functions. It's very bash heavy, so it's a good also inspiration for some bash commands that you might want to run. Then actually, if we go to the end, we will actually see what is happening. So here, for example, we see that they will set Docker specific configuration already by default if you are running on Docker. So you can see, for example, that they will set the default page cache size to 512 megabyte, the default server listen address to 0000. So this is what is allowing not having to set anything here for the network. So the container will already start listening to the world. Other things, they will apply configuration settings, set the initial Neo4j password, etc., etc. I will not go line by line here. I will just give a small summary later of everything that is happening. So here I have an explanation, small explanation of what the entry point is doing. Right. So first, it will make sure that the directories have the correct permission. So it will use the Neo4j user and the Neo4j group for the permission. It will make sure that if you specify the enterprise edition for the image, you did accept the license agreement. Otherwise, the Neo4j container will not start. If you did mount some volumes for data or logs, it will check the file permissions are correct so that it can read and write from those directories. It will load the plugins if necessary. We will go later in the session over the plugins installation. It will set Docker specific configuration. So mainly the lock rotation policy to 100 megabyte of size, page cache size of 512 megabyte, default server listen address to 000, and if also some cluster settings. So it will actually listen to the host name of the container. We'll apply configuration setting that we provide. Here, we didn't provide any. It will set the Neo4j initial password. Very important. It will only work the first time the container started and the database was created. I will explain why later. And then it will execute the Docker containers command. Right. So why the setting of the Neo4j password is only the first time is because compared to way before where it was stored in a file, today the configuration of the Neo4j users is stored in the system database. So actually, if you want to have a quick overview of what it would look like, you would have actually in the system database a user node with Neo4j, a hash of the credentials, if the password change is required, and the roles of the user, so generally admin. Right, so you cannot change this. This is why it's only permitted on the first time, right? So yeah, this is a small summary of what is happening when the containers start. Now we will stop this container here. Docker compose down and dash volumes. What is doing this? It will actually delete this thin right layer that we saw before, right? So every data that was stored, as I explained, it will copy the neo4j.conf file because we are making changes. It will copy the data directory because the system database is created, the neo4j database is created, etc. So all of this will be in the thin right layer. So we delete this layer here by using dash volumes. Actually, if we don't delete this layer, this is what allows us to restart the container and not lose any data, right, as well. So if we don't explicitly delete the volumes, we don't lose any data, right, until the volume is deleted, either by yourself or if you would use a system prune command, for example, right? So here, all right, let's go to the next section. So accessing the container to understand how the container is running, right? You have the host virtual machine, which is my laptop, but it can be a EC2 instance or whatever, or even a Kubernetes pod. And you have the Neo4j container, which is actually an isolated VM with its own process tree, its own network, etc. Right? So inside that container, we have the /data/logs, which are in the thin layer. And we also have 7687, 7474 ports exposed from the container. And if we look at the Docker Compose here again, right, we can see that we map those ports to the host ports. So this is what is allowing me to specify localhost 7474 or localhost 7687 for Bolt, and it will be routed to the container port 7474 or 7687, right, here. Couple of commands for controlling the container. Let me go here, 4, right? So you can start the container. So let's start the container again here, Docker compose d. And as I said, I will not use the full command for the logs. I have a small shortcut here. So neo4j is starting, and it will be started, yes, in a couple of seconds. So if I refresh the page, we can see it started. Right. If I need to access inside the container to inspect, we can attach actually a shell to the running container, right? So if I don't specify a name for the container explicitly, when running with Docker Compose, it will actually take the current directory as a prefix and the name of the service and 1, because you can have more than one instance of the same container. So let's copy this command here. Right, I am inside the container, so you can see we switch from dollar to hashbang. So now if I would just list where I am, LSL, we can see license. We can actually see inside the Neo4j Neo4j directory. So if we look back to the Docker Compose, so let me double click here to the Docker file. Sorry, we can see here the work here is the Neo4j home. This is why when we attach a simple shell, we land directly in the work here. Right? So here we see that we have the data directory that is actually same linked to the /data volume, logs directory, same link to logs volume. We have a couple of other directories like import, labs, metrics, plugins, etc. Right? So if we would look here in data, data, CD data. You can see that when the container started, it created all those directories. And as you can see, the ownership of those directories is on the Neo4j user. It's very important. We will see later. Right, there is another thing that I want to mention is that if we look in the startup directory inside the container, we can see there is the entry point, which is actually run when the container starts. There is also Neo4j Labs plugin.json that will give an explanation about later in the session. Right, so if we need to investigate the logs, so we can go to logs here. So of course we can attach a shell inside the container and, for example, tail the query log. Right, so we can see here, those are the queries that are run when you launch the browser to get the statistics of the node labels, etc. But this is not really practical to have to execute a shell inside the container just to be able to see the logs, right? So there is an alternative, right, which is that you can, instead of running a shell, you can actually pass a command that will be executed and will override the default neo4j command of the Docker of the container, right? So you can go here. Sorry, it will not override it. It will just execute it. So here, if I run this command, I don't need to SSH or to execute a shell inside the container. I can just here have the same debug.log or query.log without having without having to leave my host shell, actually. So it's much more easier because you leverage all the facilities of your own shell, like history, auto-completion, etc., your own shortcuts, etc. This is why I have a lot of shortcuts. Right, so now if I need to restart the container, I can just do docker compose, restart, and pass the name of the service. So the name of the service is here, the service neo4j. So in the same Docker Compose, you can have multiple services, but here I pass the name of the service. Right, so I just do compose restart neo4j, and if I check the logs, you see stopped, and then it will restart. What is very important is that when you restart, it doesn't, again, it will just restart the container, preserving the same configuration that was provided when the container started the first time. So if you do any changes to this configuration, it will not be applied. So actually we can check here. If I just remove the port mapping definition and I restart the container, I will still be able to access Neo4j because the configuration didn't change at all. Right? So if you want to have the configuration changed, right? So for example, let's say we leave it here. You can do docker compose up-d. What will happen with up-d, mainly with up, is that it will recreate the container with the new configuration, but will preserve again the volumes, the thin write layer that was created when the container started, right? So here, let's try first here. Let's create, for example, a node. Okay, we will now apply the configuration. So let's do here, docker compose up-d. So we remove the port mapping. So what we do expect now is that we cannot access Neo4j anymore from the host, actually. Right, I cannot access it. So now I will reapply the ports mapping. Start again. And what I do expect is that the node I did created to restart before, to recreation before, will still be existing. right? Let's go back here. And if we look here, we still have our node, Neo4j node that is existing. All right. Now let's check maybe no other commands. So yes, we already discussed Docker Compose, down volumes, remove everything. All right. Let's clear this one and move to the next section. Right, mounting volumes. Right. So as we saw, Neo4j expose data in logs, layers. So what we will do now is that we will actually mount a host directory as a volume to data and to logs so that we can keep a copy. The IO will be more performant. And also, if I would use dash dash volume when tearing down the container, it will never be destroyed, right? So it's not a layer anymore. It is really part of the host system. So let's check first at the Docker Compose. You have here volumes. So I mount the current directory slash data to the slash data volume inside the container dot logs to slash logs, right? So if I run this now, Docker Compose upd. Oh no, why I have this here? Neo4j started again, but now if I look here on my local directories, I can see that all the data that we saw before was created inside the container. So the system databases, Neo4j database, is now available in my host directory, right? So this means that I also don't need to at all to attach something to the container to inspect the files. I can just now do till f logs query log, and there are no logs because we never opened here. Okay, now we see the logs, right? So now they are available inside my host directory, and if I tear down the volumes, actually, let me create a node here. Create. Okay, use the history, right? If I would tear down the container, delete the volumes, right? The thin right layer. You can see my data is actually not disappearing. I can keep the data, right? Also, the data is accessible. If you keep in the thin right layer in the Docker layers, it is very, very hard to inspect the content of the layer, and it is very hard to share the data as well, right? So, so here, if I restart the container, started, I refresh the browser, and I should see my node here. So this will actually be the most confident way of never losing data is to use properly a volume, right? So now we'll get on the container again, and we'll move to the next section. Configuring Neo4j. Now this will be very interesting. What I will do, I will comment this line. We will go over later, and I will provide a setting here. So what is important, when you look at the Neo4j configuration in the documentation, for example, in the operations manual, you will have the format that is the same as the neo4j.conf file that you find if you download Neo4j tarball, for example, which is dot and 1 underscore. When you are using Docker environment for configuring the container, you need to first prefix the name of the setting with Neo4j underscore, And then you need to replace dots with 1 underscore and replace underscores with 2 underscores, right? So we saw in the entry point that it was actually applying the configuration settings from the environment to the Neo4j conf file, right? So actually, I will run this now. Docker compose. No, I am in the wrong terminal here. Docker compose upd. Why? So it did start, and now let's go inside the container and inspect the neo4j.conf file. Right, so I will first check is the name of the container that is running, copy that, and I will do docker exec it sh. It's why I need to go inside the container is because I have nothing that is actually mounting a volume for the conf directory. Right, so if I check here, I go to the conf directory, and I will do cat neo4j.conf. And we can see that our setting is actually added at the end of the neo4j.conf file with the right neo4j.conf format. So it will actually transform back your underscore, remove the prefix, etc., and add it at the end. Right? Why at the end is because it makes sure that the latest setting is taken into account. But there is one thing that we will see later about this. Right. So here you can also see that this was done in the entry point. So I explained that the cluster settings are using the container hostname. So you can see here, this is the result of dollar parenthesis hostname. And here our setting is there, right? So what would happen if we would have a Neo4j a conf directory? So let's remove that one. It's from a previous dry run. I will mount a volume here with the conf directory, and I will copy. This is the original neo4j.conf. I will just create a brand new neo4j.conf with the default value here. Right. So we can see at the end of the file, there is nothing. So what we'll do, we'll mount the conf directory to the configuration directory inside the container, and we will see what is happening. And before seeing what is happening, let's find the setting here that we're using here. And neo4j.conf, I will find the setting. I will uncomment it, and I will say instead of it will just be 1024. And maybe I need to tear down the container as well before. Okay. I think I did that in the wrong one. No, I'm in the correct one. All right, so now let's take back the Docker Compose. We have a volumes mounted, and we apply a setting, but we also did change that setting in the neo4j.conf file that we will mount inside the container. So let's see what is happening. So we'll start the container. If we look at the neo4j.conf file here, if I look back for that, you can see there is only one setting. So actually, if our setting was uncommented, it will be removed from the conf file, and what you provided in the environment will be appended at the end of the file. Right. So what is happening is that you do have precedence. So first, it will take your own neo4j.conf, and then it will overwrite with what you provide in the environment. All right. So Let's tear down the container and let's go to the plugin section, which is one of the Docker Compose down. Very interesting one. So here, okay, plugins. So we saw that there is a Neo4j Labs plugin file in the startup directory of the container. What this file is actually a dictionary of the plugins you can provide in the Neo4j plugins in your Docker Compose here, right? So it will tell, okay, for example, in case of epoch, if you specify epoch, this file is already in the container. So you just need to take the file from the container and execute this setting as well. If you would take n10s, it will actually check the versions file in the directory. So actually, if you look at it here, you can see, then it will check for, okay, for Neo4j 5.0, I need to download the jar from there, and it will download the jar, install it, and also apply those settings, for example. So if I do Docker Compose D again here, and I check the logs, right, we can see here, installing plugin Graph Data Science from the varlib, it's already in the container. However, for n10s, installing plugins from, and it fetched the URL from the versions.json file, right? So this is important because often when a new Neo4j version is out on Docker Hub and you try to install plugins, sometimes the versions.json file is not up to date, for example, for n10s, and you will have Neo4j not be able to start because you cannot find the version in the versions.json. So be aware of this because often you have to wait 1 day or 2 to be able to have the plugins aligned as well, right? So, and actually, if I go now to Neo4j and I just do show procedures, you can see is there epoch, GDS, etc. Right?
Sorry to disturb you, Christoph, but there's about a minute left.
Yes, sure. And I'm good. So 1 minute left. So let's tear down this container. I will just show a small trick that I found to create files, to create custom images with our own plugin. So we saw this this versions, Neo4j Labs version. So actually I create my own Docker file from Neo4j Enterprise, and I will copy my plugin jar into varlib Neo4j Labs myproc.jar, for example. And I will actually, with JQ, modify the Neo4j Labs plugins.json that is in the container, and do the same trick that they do. So I provide the location, I provide the properties that needs to be added, etc. So now if I go here, I just do Docker Compose pubd, right? And I check the logs. We can see that it will install my own plugin. Ideally, let me check the Docker Compose. Yes, my proc. So not Docker file. Here. So where is it? Okay, here applying default values for plugin and installing plugin by proc from actually the directory I created. So it's a neat way. It's very easy to do by just using JQ to add in the original versions.json file the correct things to do. So we just leverage what Neo4j did for their own plugins to create our own images. And that's it. So I think I'm done on time.
All right, what a great session. So much content on Docker. So I think that we had some interest in knowing, will this tutorial be available somewhere on GitHub or anything like that?
Yeah, I want to share. Maybe I can. Is my slides still sharing or not?
I can put it up there. It's fine.
Okay, so I will share like all the content of this here into GitHub as well. But also, if you go to bit.ly neo4j-docker-compose, you will land to one of my repositories, which contains a lot of examples of how to run Neo4j in different configuration with Docker Compose. So, for example, 3-core cluster, Neo4j 5 autonomous cluster, Neo4j 5 single, with server-side routing the whole time, read-only replicas, etc. So you will find a lot of examples there.
That's perfect. That's perfect.